Good evening, Ananda. This is Dr. P. Srinivaslu, currently working as Associate Professor in National Calendar Engineering. In YouTube lecture series, the subject is probability theory stochastic process. In this, the concept is transformation of random variables. So, if we consider n random variables, that is xn is equal to here n takes 1, 2, 3, and so on up to n. And you see, yn is equal to transformation means we are converting from one domain to another domain. So yn is equal to transformation of x1, comma x2, comma and x3, and so on xn. And suppose we have transformed from the random variables from xn set to yn, and again we want to convert into original domain, like in Fourier series or Fourier transform, Laplace transform, and jet transform. Usually, we are going to be convert a continuous time signal into time domain signal into frequency domain. And after analyzing the signal or analyzing the system, again we need to convert that frequency domain signal into time domain. The same concept. We are going to be convert a random variables, a x1, x2, a set of random variables in x1, x2, x3, and so on. We are going to be convert into yn, and again we need to inverse of this one. We are going to get again our xn series. So that is the idea of transformation of random variables. Now, if you see y is equal to transformation of x. That means, suppose here the random variable n is equal to 1. That is a single random variable I am considering. So I have converted, we have transformed the x random variable into the y. And after transforming, again, whenever we require, we need to retransform it to x inverse. So x is equal to t inverse of y. Now, whenever there is a random variable, generally there is a density function. Suppose fy of y. In this fy of y means density function of y random. That is, already we have a random variable x. Now we can write it is a fx of x. Here, this y we are going to be write again into inverse. X is equal to t inverse of y. Fx of x is equal to t inverse of y. So t inverse of y, that is going to be right here d by dy into t inverse. Now in general format, fy of y is equal to, that is the density function, marginal density function of y is equal to, or single random variable density function y is equal to fx of x into dx by dy. It is for n is equal to 1. Similarly, if you want to write n is equal to 2, so if we consider two random variables, x1 comma x2, and transforming random variable is y1 comma y2. That means x1 is transformed to y1, x2 is transformed to y2. And then the corresponding density functions, that is f y1 comma y2 of y1 comma y2 is equal to fx1 x2 of x1 comma x2 into, we are going to be differentiate this x1 with respect to y1 and x1 with respect to y2, x2 with respect to y1, x2 with respect to y2. So it is like a matrix form. In a way, for generalized case, we are discussing with n random variables. But throughout this subject, through PTSP subject, probability theory subject, we are going with only two random variable case. If you go for n3 or 4, it is the somewhat complexity is increased. So the idea of transformation we got now. We are converting from one domain to x to y, and again, whenever we require, we need to retransform inverse of this one. So next concept is linear transformation of Gaussian random variables. Now, linear transformation of Gaussian random variables. If we consider n Gaussian random variables, that is y1, yn, that means the set of random transform random variables, and already existed random variables, Gaussian random variables, x1, xn set, x1 comma x2 comma so on xn. Now, if we write that equation, linear relationship between transformed one and already existed random variables. Suppose if you write y1 is equal to, in terms of x1, that constants like linear combinations, a1 x1 plus a2 x2 plus a3 x3 and so on, an xn. Similarly, if you go for second transformed random variable, y2 is equal to a1 x1, a1 x1, a11 x1, sorry, here a11, a21 x1, because y2 transformed is y2, a21 x1 plus a22 x2 plus a23 x3 and so on, a2n x. Row is common, columns are going to be changed, and so on. That concept is extended for n random variables. So instead of writing these equations in mathematical equation, better we can write these are in matrix form. That is somewhat easy compared with the general linear combinations of equations. So we consider the transformed random variable is y1, y2, y3 and so on, yn in a single column, and corresponding coefficients, that is first row a11, a12, a13 and so on, a1n, a21, a22, a23 and so on. They were going to get a matrix, a coefficient matrix, and corresponding original existed random variables x1, x2, x3 and so on x. So it is we see this transformation, whatever we are transforming, so that is coefficient elements are there. These coefficient elements is going to be right like a T transformation. This T is equal to whatever the linear combination of elements that is going to be right in a matrix form, like a11, a12, a13 and so on, a1n, a21, a22, like that if you form a matrix. Next, now total transformation of linear transformation of these Gaussian random variables. If you write y is equal to, this is a transformed random variable matrix is equal to T transformation and x existed random variable. Now again, if we want to retransform from y transformed domain to original domain, x is equal to T inverse of y. It is a matrix form. Now, similarly, the same equation we are going to be right with the deviation of mean. Y minus y bar is equal to T, wherever we have a y, that is replaced with y minus y bar. Wherever we have a x, that is replaced with x minus x bar. Now again, from this transformed domain, again we need to calculate inverse of this one. That is x minus x bar is equal to T inverse of y minus y bar. Now, definitely, whenever we are performing this inverse transform, we are going to get in the matrix new elements that is going to be represented here. Original transformation there is a series is started with some A11, A12, like that we have assumed. Now, here, the inverse of this one, we are going to be write these elements like B11, B12, B13, and so on, Bn and first row and second row, third row, like that. How many number of transformation uh, random variables are there? So that much of matrix we will get. That is size is depends upon the random variables. Now, if you want to write this equation from this matrix form, suppose if you want to write for x1 is equal to, you will get like bi1, bi2, bi2, y2 plus and so on, bin, yn. Generalized equation if you write. Now, that is, we are going to be write this inverse operation for generalized case like xi, I indicates here takes 1, 2, 3, so on, and bi, bi1, y1, bi2, y2 plus like that. Similarly, wherever we have a this random variable xi, it is going to be divided with this mean xi minus xi bar is equal to bi1, y1 minus y1 bar, bi2, y2 minus y2 bar, and so on, bin, yn minus yn bar. And we know whenever there is a inverse transformation, so it is dxi by dy I, dy is equal to d by dyj inverse transformation, that is going to be right bij. So this a determinant matrix, we are going to calculate T inverse, that is J is equal to determinant of T inverse, that is equal to 1 divided by T. Now already we have seen this correlation of any two random variables, that is a Cxi xj is equal to expected value of xi minus xi bar into xj minus xj bar. Now this same equation, whatever we have a this linear combination of transformation random variables, now we can write, we have a formula for xi, that formula here we can replace with this bi1 into y1 minus y1 bar and linear combination of this. So like that, we can frame a generalized mathematical equations. So the generalized mathematical equations are k equal to 1 to n bik and m equal to 1 to n bjm and expected value of yk minus yk bar into ym minus ym. Now finally, this cxi cxj is equal to k equal to 1 to n bik, m equal to 1 to n bjm cyk ym. That is correlation between two random variables here. So from this, we can give conclusion. This cxx, cxi, cxj is the ijth element of covariance matrix, and similarly, this the kth element of the this cykym or kth element of the covariance matrix of cy. Now this bik is the kth element of T inverse. So finally, if we form a covariance matrix from this, we can write cx is equal to T inverse into cy T transpose into E inverse. So R cy is equal to T into cx into T transpose. So the inverse of cx is cx inverse, if we write, The inverse, whenever there is a T inverse, it can be modified as a T. Cy is modified as a Cy inverse, and T inverse is modified as T. So then you can calculate this Cx inverse. This Cx inverse we are going to be obtained. Cx inverse is going to be obtained is equal to this T transpose into T is going to get T square and Cy into inverse. So finally, this is going to be right in density function, Gaussian n random variable density function. So that is going to be like this. Density function formula is like this. So it is about linear transformation of random variable. So somewhat lengthy analysis is there, but anyway, we have an idea about Gaussian random variable. From that Gaussian random variable, single random variable, that concept we are extending into linear transformation of Gaussian random variable. The simple idea is a set of random variables we are going to be converted into new domain, and then again we are going to be inverse operation, and we will get the original transform. So whenever the random variables are increases, so we are going to be write like a matrix form. So that is somewhat complex mathematical equations. But if we concentrate on this, we can easily obtain this equation. The mathematical form, the theoretical case, it is somewhat difficult. But whenever if you go for problems, there may be some two random variable case, we can easily understand. Thank you. We will see the next.